Okay, we're going to look at the last section here this week. I know it's a heavy week. Okay, so just hang in there. Okay, and we'll go through it this afternoon. Phase changes and global energy transfer. So phase changes that occur in the hydrological place. Have we covered this? Water absorbs a lot of energy when it evaporates. Water releases a lot of energy when it condenses. Large energy transfers can produce thunderstorms, even hurricanes. Yeah. Okay, this is where we are. Okay, so we're going to combine specific heat capacity with heats of fusion. As a substance heats or cools, its particles gain or lose energy. When there's a change in temperature, we use that formula, Q equals mc delta. And when a substance undergoes a phase change, we use this formula. Both of these can occur in a single heating of a substance, the warming of ice. Now take a look at this. Here is my ice. So because there is a change in temperature here, we use Q equals mc delta T. But then once it gets to 0 degrees Celsius, we use the second formula, Q equals N times heat of fusion. And then when the water warms up, when it goes from 0 to 100, we use delta T again. And then when it goes from liquid to a gas, we get a, when it goes from a liquid to a gas, sorry folks, right here, we use M times the heat of vaporization, okay? Um, and this should be N, number of moles times the heat of vaporization. And then when we get another change of temperature, when it goes into steam, MC delta T. Here it's warming up. We get a phase change. Here the water's warming up again. Phase change. And the last time was heating up as well. So given the values below, determine how much energy is required to turn 250 grams of ice that has an initial temperature of minus 20 into steam having a temperature of 150 degrees Celsius. Okay, now this is going to be tricky for me to answer in such a small space. And it's really something that we want to spend a bit of time trying to come up with this afternoon. But let's just sketch this out, for example, here. Given the value, determine how much energy is required to turn 150 grams of ice that has initial temperature minus 20. Okay, so there's my graph. Into steam. Whoa. Okay. Um, we have got a fair bit to do here. That's minus 20. That's 0. That's 100. And that's 150 degrees Celsius. Okay, so we got to do two calculations with phase changes here and here. We go Q equals N times heat of fusion, and Q equals N times heat of vaporization. Okay, we are going to have to do two of those plus one, two, three calculations. The calculations 1, 2, and 3, we use Q equals mc delta T for, okay? And for these other two, we use Q equals NHF in both of those. So this is a real challenge problem, okay? And for heat of fusion, we're going to use 6.01. Heat of vaporization, we're going to use, okay? And heat capacity of steam, we're going to use that equation number 3. Heat capacity of water, equation number 2. Heat capacity of ice, equation number 1. The only other thing you have to do here is N equals mass over molar mass. And we've got 250 grams. And the molar mass, like we calculated last time, is 18.02. So the number of moles that you're going to use in equations 2 and in equations for the heat of fusion and here and there is going to be 250 divided by 18.02. okay, which is going to leave you with 13.87 moles. Okay, so go ahead now and do one, two, three, four, five calculations. Add them up. Calculation one plus calculation two plus calculation three plus calculation four plus calculation five. Add them up for the total amount of energy needed to convert 250 grams of ice into 250 grams of steam at 150 degrees Celsius. So spend some time with that one, stop the video and see what you come up with. And there's your answer, 787 kilojoules we should arrive at. Okay, so we've looked at that and we will go through those answers this afternoon.